Okay. You're going to have to pardon me if I get quieter during the course of the lecture. I caught the plague that's going around, so I'll keep my distance. So we're moving on from conduction. We've spent up till now talking about how heat travels through solid and stationary objects, right? Media that are at rest, which is really important, but we've sort of glossed over these ideas of convection and radiation to date, which are equally important for a lot of applications in engineering. So what we're going to do next is work on really picking apart these convection behaviors, right? What goes into that H that we just sort of magically plug into the Newton's law of cooling in order to get heat fluxes when you have some fluid flowing past a surface. So 19. Today is going to be focused on getting us centered on this topic of convection. Namely, what we're going to talk about today it's going to be a broad description of what convection is, how we talk about it. We'll talk about velocity and thermal boundary layers. And we'll go into the difference between local versus average convection coefficients. So, first thing, let's lay down a definition that we'll fall back on describing convection. Okay, we'll go ahead and choose to describe it as convection as heat transfer between a usually stationary surface and a fluid adjacent to that surface. And oh, come on, there we go. And when we talk about convection, right, we're talking about the case where that surface is usually the boundary to some solid object. So you'll have a solid over here, and you'll have a fluid over here. So what goes on in convection is really two different mechanisms, okay? And we can see those by investigating the name convection. If we take this first part, right, this is sort of a clue that there is both conduction, and the second part tells us that there's this thing called advection. So conduction is, right, it's that diffusive spreading out of heat. So if this boundary, for example, is warmer than the fluid next to it, the idea is some of that heat is going to be transferred to the fluid via this diffusive action of these molecules running around and bumping into each other. Okay? This is especially true because, and we'll talk about this in a second, right? Whenever there's a fluid moving past an object, what do we know the velocity of that fluid is at the object? 0, right? There's this thing called a non-slip boundary condition. And so if the fluid has a 0 velocity right where it meets this solid boundary, then the only way for heat transfer to cross that initial boundary between the solid and the fluid is by conduction. And from there, the advective term starts to pick up. So advection, choose to describe as transport. So convection is the combination of these two things, some spreading out of heat and some transport of heat by the bulk motion of the fluid. Okay, if we consider this fluid to be flowing past the object. So besides thermal energy, right, convection governs a variety of different phenomena and these are going to be a secondary focus of this class. Besides thermal energy, there's also this thing called species transport, which besides thermal energy, we can have mass convection, or convection of concentrations of some type of matter, which in this field are called species. So if you think about, for example, a stream, right, that's flowing down out of the mountains, if it routes itself through a portion of land that has particularly iron-rich soil, okay, it would make sense to expect that the iron levels, suspended iron levels in the water coming out from the end of that stream are going to be higher than the iron levels going in, right? Because some of that solid matter, some of that iron concentration has diffused and advected into the flowing water. So it's been transported as well. It's an identical set of math. It's just a different physical phenomena. So the tools we're using here are also useful for analyzing the way that this species transport occurs. But so back to thermal energy. If we have some wall here with a temperature T sub S, and we have some fluid out here that has a temperature T infinity. Okay, we've been over this before, but the idea is, of course, our heat flux and our heat rate are given to us by this thing called Newton's law of cooling. So heat flux says that Q double prime N is equal to H times T S minus T infinity, where N is pointing out of our solid object. So this is telling us, right, our signing here says that if the surface temperature is higher than the fluid temperature, heat is going to leave from the solid into the fluid. Makes sense, right? And then the heat rate, heat rate, Q, N, is equal to, if we were to integrate that heat flux over the entire surface, right, this would work out to A, H times Ts minus T infinity dA. So if we know, right, it's possible that the surface temperature, that the fluid temperature, and the convection coefficient itself could all change over the surface. So we need to have some insight into the way that those behave across this surface before we perform that integral and actually get out a useful heat rate in watts, okay, which is really the thing that we're usually interested in at the end of the day. So this is a little bit more review from that first week of class, right? Convection comes in a couple of different flavors. The first we'll go ahead and refer to as forced convection. And this occurs if you have some, let's say we have some surface here that has a fluid flowing past it. The idea is forced convection has fluid flow externally imposed. That is, either the flow is moving because it's being driven by some upstream pressure, like a current, if you were to stick something hot into a moving body of water, that would be considered forced convection because the pressure field upstream is driving the flow. Other examples include fans, pumps, right? Generally, most of the things we think of as active cooling systems. Your laptop fan kicks on. What it's doing is it's moving over to a forced convection regime. So with forced convection, right, the idea is heat that's coming off of the object is going to be transported away from the object very quickly. Free convection, on the other hand, has fluid motion induced by buoyancy as the fluid is heated, or as the fluid temperature changes. So kind of pictorially, what that would look like is you have heat coming up off of the object, or thermal energy coming out of the object. It's going to warm up the air, cause the air to rise, or if it's water, right, a slight temperature variation, or sorry, a slight density variation will result from large changes in temperature. So some of that warmer fluid, not air necessarily, will rise, and cooler fluid will come in to take its place, and you end up with this sort of cycling of the flow. Something I've noticed is whenever we turn on this projector, right, at the beginning of the day, you see this sort of roiling light pattern. And I think this is actually a really good illustration of what free convection looks like, because kind of off the bottom here, you can see where the bottom of the projector would be causing heat to flow upward, and you end up with this sort of recirculating pattern of flow. This, by the way, is similar to a kind of flow visualization called Schlieren visualization. It is as the density of a fluid changes, its index of refraction changes, and so it will create little shadow patterns that indicate the way that fluid is moving. As another little anecdote, is free convection. I had a buddy back in college that let's put this in automotive terms. Forced convection, right? The coolant pump in your car that cycles coolant through the engine and through the radiator, right? That's going to be a forced convection case, right? Because it's being pushed through that system forcibly by some external pump. On the other hand, I had a buddy in college that decided to make a coffee maker out of his bike's cooling system, or to add one. Basically wrapped a bunch of copper wire around and into the cooling system of his motorcycle, and created a little hot water tank. And the idea there was, as the water was heated in the copper pipe, it would expand very slightly. That buoyant force would tend to make it rise and pull in cooler water underneath. So you got this sort of naturally recirculating system that will eventually bring hot water up to a boil and had a little coffee pot attached to it. So that would be a case of free convection, right? Because the fluid motion there is being imposed by the temperature change itself. So generally, forced convection, much more efficient at getting heat out of there. Free convection has the obvious advantage of, right, if we're talking about a consumer product, you don't need fans, you don't need pumps, you don't need a flowing fluid. So, the idea here, and what I want to take away from this, is that convective heat transfer is tied closely to the way that the fluid next to the object is moving. Right? The behavior of that fluid's velocity is going to tell us a lot about the way that heat transports into the fluid and again gets either pulled away or cycles out through this free convective process. And so this leads naturally to the idea of, and cue the groans, boundary layers. We talked a lot about certain types of boundary layers in fluids. Right? And so we're going to do a quick little review of that. So the first is the kind you've all seen before, this thing we call the velocity boundary layer. The idea here is we're going to have some surface and there is some velocity upstream, or there's a fluid that's approaching the surface with some velocity that we'll call u infinity. We'll say that x equals 0 is located at the upstream edge of this surface, or this flat plate. And what occurs, right, is as this this fluid encounters this plate, it's going to the fluid immediately adjacent to the plate is going to stop. Right, its velocity is going to be arrested by this non-slip boundary condition. So you're going to have this non-slip, or u equals 0 at y equals 0, right, where y is defined away from the plate. So the fluid is being slowed down to 0 at the plate. It in turn slows down the next adjacent fluid particles by action of shear stress, and so on and so forth. And so you get this gradual retardation of the flow next to the solid object inside of this layer that we call the boundary layer. So a second here. So inside of this boundary layer, we know that u is going to be less than u infinity, right? Whereas outside of this boundary layer, we know that u is going to be about the same as u infinity. So that's where we make the distinction. Usually the edge of this boundary layer, this green boundary, is the collection of points where u is about 99% of the free stream velocity. And so we call this there's a thickness, if you will, delta, and which is a function of x. So some kind of summary notes here. Shear stress it causes fluid near the wall to slow down. And the behavior, the thickness, and the overall flow regime of the boundary layer is governed by this non-dimensional parameter known as the Reynolds number, where Reynolds number is equal to, as a function of x, is equal to u infinity times x over the kinematic viscosity of the fluid in question. All right, that is so that's it for our quick little 5-minute review of velocity boundary layers. I want to talk about the sort of its sibling, which is the thermal boundary layer. So similar premise. You'd say, suppose we have some surface here, and we have upstream, let's say we were to plot the temperature of the fluid upstream. The idea is T infinity, so all the fluid upstream that's flowing from left to right has a uniform temperature T infinity, and this solid surface here has a uniform temperature of Ts. So Ts and T infinity are constant. Okay, those are just fixed numbers that we're assuming to be totally unimpeachable. So what's going to go on is as the flow encounters the plate, similar to the non-slip boundary condition, we're going to have a thermal equilibrium condition that says right at that surface, the fluid has to take on the surface temperature. Okay, those molecules that are in contact with the surface have to reach the thermal equilibrium. So we're going to end up with this region of changing temperatures that we know as the thermal boundary layer. So what that's going to look like is, so let's say that this is Ts, this is T infinity, so I want you to understand that these arrows in this line here are indicating not the velocity any longer, but the sort of the magnitude of the temperature. So the saying is, right, that inside of now our thermal boundary layer, the temperature is varying between the surface temperature and the free stream temperature. And so once again, analogous to the velocity one, we would say that we have some now delta T, which indicates the thickness of this thermal boundary layer. And inside, we know that T is going to be, it's going to reside between the surface temperature and the free stream temperature. And outside, it's going to be approximately equal to the free stream temperature. Let me move some stuff around here so it's less crowded. So, our notes here would be that temperature varies between T sub s and T infinity inside of delta T x. We can also get some insight by looking at these two things together. For example, right, if convection is a combination of conduction and advection. As I said before, we know that right at the wall, the velocity is equal to 0. That means that the only heat transfer mechanism, or between those two, right, the conduction and advection, the heat transfer mechanism that's going to dominate right at the wall is going to be conduction, right? Because the velocity is 0, there's no bulk motion. It's only that molecular diffusion of heat that causes thermal energy to transfer into the fluid. So near wall, the velocity approaches 0. Conduction is dominant. And far from wall, velocity approaches infinity. Advection becomes dominant. So once again here, kind of the takeaway from these two sketches is that the thermal boundary layer and the behavior of the heat transfer in the thermal boundary layer is dependent on the velocity boundary layer. We can't consider them to be totally separate things. The other thing I want to point out is that, and this is important that you note this, the thermal boundary layer thickness is not necessarily the same as the velocity boundary layer thickness, right? So these two should not be confused. One can be a lot thicker than the other, and what determines the relative thickness of the two are going to be these dimensionless parameters. In one case, the Reynolds number, And in another case, we have another different set of numbers, such as the Nusselt number and the BO number, etc. So that's what we're going to be talking about in these chapters, is the way that this behaves. We'll be assuming a lot of things about the velocity boundary layer. We'll do a little bit of calculation with the boundary layer equations, but not a whole lot. So what is this, like, why bother, right? Why does this matter to us? The answer is that if our goal, right, is to come up with a number for Q, to do that, we have to know what H is doing. And H is going to be a direct consequence of the behavior of the fluid inside of this thermal boundary layer. So it's important we understand what that physical behavior is. Behavior of the convection coefficient H. So I want you to consider, again, we're going to set up this similar sort of scenario where we have some surface. We'll say that this is Y. We'll say that X is measured from the upstream edge of this surface or this plate. Okay. We'll say that this, again, has a uniform temperature of Ts, and once again that we have flow at T infinity with a velocity of U infinity. Oh, come on. So, taking what we concluded from the above sketches, we're going to have a couple of different ways that heat transfer is occurring from this surface to the exterior fluid. The first is, as I said, right here next to the wall, we are going to have that U is approximately 0. That is the velocity in the velocity boundary layer is going to be very, very small. So if this here, this blue line here is indicating the velocity profile, okay, so it's going to 0 at the wall. So as our bundle of thermal energy leaves the wall, right, in this wall it's traveling due to conduction. We have Fourier's law. When it hits this boundary between the solid and the fluid, its initial travel into the fluid, because the velocity is 0, is going to be through conduction. So in that really, really tiny layer, that infinitesimally small layer of fluid that's stuck to the wall, we're not in a convective transport regime yet. We're still doing conduction. Okay, so conduction in infinitesimal layer that is stuck to the wall. So we would write Q double prime N equal to negative KF T dy y equals 0, right? Where case of F is our conductivity of the fluid, not of the solid anymore, right? Then as we travel outside of that infinitesimally small layer, once we're at any distance from the wall that is y not equal to 0, at any finite distance from wall, or if we want to talk about across the remainder of the boundary layer, right, we're going to have that Q N is equal to that H times T Ts minus T infinity. So the idea is that thermal energy leaves the solid object via conduction. It travels into the fluid via conduction in a very small layer and then gets sort of transmuted into convective transfer. So these two quantities have to be equal to one another. And we end up with negative k sub f t dy y equals 0 is equal to h ts minus t infinity. All we're saying is, if we're to do that surface energy balance in that thin layer of liquid or that thin layer of fluid, the sum of the thermal energy in has to equal the sum of the thermal energy out. The reason that this is important is because now if we solve for h, we end up with h equal to negative kf t dy at y equals 0 divided by ts minus t infinity. And this kind of unlocks some nice, some good physical intuition. We need to make sure we understand what this expression is telling us. Item 1. What happens to the, or as to say, as x increases? So as we sort of travel along the plate, what happens to the thickness of our thermal and our velocity boundary layers? They're going to get larger, right? They're going to expand. So delta T grows. Okay? So the thickness of that thermal boundary layer is going to increase. What happens to this Ts minus T infinity? Nothing. We've said at the beginning of the problem we're going to assume that both of those are uniform constant numbers. So we end up with Ts minus T infinity remains constant. So if we say, all right, we have the same temperature jump, that Ts to T infinity, occurring across a increasing distance, right, that thermal boundary layer, then that tells us that the gradient, right, that slope of the temperature has to be decreasing everywhere. So what this means is sort of by intuition and by reasoning that dt dy is going to decrease. So the takeaway here is that if dt dy decreases in magnitude, right, and everything else in this expression remains constant, and it says that h will also decrease. So as you travel along this plate, your local convective heat transfer coefficient, H, is going to start out at some value, right? But it's going to diminish as you go further and further along the plate. So this is the problem with, well, this sets up what's known as the convection problem, right? Figuring out H when H itself depends on the temperature distribution and the thermal boundary layer. And figuring out H is going to be the main topic of this chapter. Okay, doing all right. I promise we'll get into a couple of examples on how to use this in just a second. So as a final thing here, right, so this sets up this idea of local H, right, our local heat, convection coefficient, and we want to contrast that to the average H. So if we have some, let's say we have some object, it doesn't need to be a flat plate. Let's say we have some weird shapes, we'll say this is a potato, which is hot. and we have some flow past the potato. All right. The idea is, let's say we set up a little local coordinate system. So we say x is actually this this thing that's always measured along the surface. So increasing x means we're just traveling around the surface of the potato. We're basically kind of unwrapping it into a flat surface. We would say the heat flux, right, at x would be written as q double prime n is equal to hx times t potato minus t infinity. So we're saying is that at every position, it's going to be a matter of the local value of h. That is, that assumes that the temperature of the potato is uniform, right? Does this make sense? Everyone on board? What about the total heat rate? How many watts is this hot potato putting out? We get that by integrating. Q double prime n, so we end up with q, and is equal to the integral over the potato area of hx times t e minus t infinity dA. So we're integrating over the entire area of this object. Now, because we said that this is at some constant temperature, T potato, and that the fluid has some constant temperature, T infinity, then we can pull those terms outside of the integral, and we end up with equals Tp minus T infinity integral over A of h x dA, or Tp minus T infinity times h bar. Okay, so h bar is known as the average convection coefficient, and is equal to 1 over the area times the integral of the area of h dA. So this so we can see we have right, and we want times A. I forgot the So what we've done is we've said, right, we have our sort of our conventional Newton's law of cooling for figuring out how much heat is leaving per unit area, if we know the way that x behaves as a function of space. We can use a similar relationship if we take the average h over the entire surface of the object, across which heat transfer is occurring. So let's put this into play. Let's say that we have, as an example, let's say we have flow over a rough flat plate and experiments performed on this have determined that from experiments we know that h as a function of x is modeled by a times x to the negative 0.1. So what this is saying is that h is going to have this this behavior like this, right? It's going to be this decaying term, where A is a coefficient that has units of watts per meter to the 1.9th power. Okay, that 1.9 is just so that we have dimensional homogeneity when we take a distance and raise it to the negative 0.1 power. So what we're asked to find here is going to be the average, right, h bar between, for a section of this plate between 0 and x. Okay. And then also the ratio h bar of x over hx. So this is a little bit different than just finding h bar over the entire surface. Right? What we're doing is we're saying, say we've got air flowing past this. Let this table be our flat plate. Let this be at some temperature, fluid flowing past it at a different temperature. What it's saying is between 0 and some point, what is the average h bar over the portion of that surface that has been traversed? So what's the average so far, if you will? So the way we get this is going to be, right, h bar is going to be equal to 1 over the integration domain. Say 1 over x if we've traveled from 0 to x at some point. Integral from 0 to x of h, and we'll use a dummy variable. Instead of x, we'll say zeta d zeta. This is 1 over x, integral from 0 to x of a zeta to the negative 0.1 d zeta. It's going to work out to then a to the over 0.9 x zeta to the 0.9th power between 0 and x. Okay, so here's just our indefinite integral with our limits. If we plug x in for zeta there, we're going to end up with a over 0.9 x to the 0.9 power over x, right? Which equals 1 over 0.9 a to x to the negative 0.1. So we have something that looks a lot like our local heat transfer coefficient, right? It's got the same sort of behavior. So there's h bar as a function of x. Now if we want to take h bar of x over h of x, we end up with, right, essentially our 1 over 0.9 a to x to the negative 0.1 divided by a x to the negative 0.1 works out to just be 1.11. So what this is saying is, if here's x, here's h, we're going to have 1a this blue bar here might represent the local convection coefficient, and the average coefficient between 0 and whatever x is going to be just 11% higher than that value. Okay. Are there any questions on how we did this or what it means? It's a little odd, I know, looking at the average as a function of x, but this is also an important kind of concept to get clear, is that it's the average between 0 and whatever x is. So it's going to change as you include more and more of the plate. So what it's saying is that as h decays, you take the average between 0 and x, it's also going to decay, but it's going to remain a little bit higher than the straight value of h. I have additionally, where did I put it? One more example. I may have left it up in my office. Okay, well, I left my other example up in my office, so I'll go ahead and write it out and put it up on Icon right after this. So I will see you guys on Wednesday. I put up the module schedule, so the reading assignments for the rest of Chapter 6 on Icon, so find that in the modules section, and I'll have the homework posted sometime in the next couple of hours. Okay. Have a good one.